And we have also heard about the Newton's law. Yep. So let's say if we want to increase the heat transfer rate, all right, let's start with, say, conduction.
Yeah.
And this one for convection. Let's start with conduction first. So if you look at for conduction, if you want to have as large a heat transfer rate, and it's Q, as large as possible, what do you think would be the practical thing that you could do to increase this value? Because we know that for conduction is talking about the heat transfer across say a solid, and this solid could be cylindrical or it could be plate, and this equation governs the plate. So say for example you want to have as large a Q as possible looking at this equation. What are the things that you could do to increase Q? The delta X. Alright. Now that's good until when you discover that actually delta X is kind of like very little you could do to change. Why do I say so? If you want to cool down something, that's cooling it down in ambient air normally. Ambient air, say about 32 degrees Celsius, recently 34 degrees Celsius. So if it's not ambient air, cooling it in ambient air, then you have to artificially create an environment that's cooler, so as to get as large a delta T as possible. Alright, so there'll be this delta T that's equal to T minus there, so T2 minus T1. So if you want delta T to be as large as possible, either your T2 is very small or your T1 is very large, right? Or it could be the other way around as well. If it's the other way around, that means your T1 is over here and T2 is over there. Now you would want to increase one and decrease the other one so as to get as large a delta T as possible. And usually one of these temperature would be ambient temperature. If it's not ambient temperature, then where is the heat going to go to? Right? Say if let's say it's a hot object. So usually your temperature that you want the heat to be transferring out, that is ambient temperature. Little we can do to change the ambient temperature without incurring more energy to put into that system to make sure you have a cooler ambient temperature. So if that is your constraint, that means the ambient air is your constraint, and that side is hot. Well, you can't actually make it hotter, so as to get a larger delta T. Usually you have a hot object, and then you want to cool it down in an ambient temperature. So in a way, your delta T is kind of like more or less fixed. We say that we want the hotter side to be hotter, cooler side to be cooler, so that you get a large delta T. But we know that the hotter side, that's your hot object. You wouldn't want the hot object to go any hotter. You need to put in energy. You want the cool side to be cooler, that's your ambient air, and you can't really cool it down. So you have delta T kind of like fixed. What else could you do to Q, heat transfer rate, to make sure that you have as large Q as possible? What else could you do? What? Surface area. So surface area is given by these two surface areas. Now, what could we do to increase that surface area? Because we know if we increase that surface area, respectively, we get a large Q. So, increasing that surface area, you would have thought, just make it larger. Right? But then, the object that you try to cool it down, or maybe this is a wall partition, all this comes at a fixed size. So you can really like increase that surface area, making it larger. Because we know that if it's larger, more surface area, more heat transfer. Yes, that's right. But practically, your object is that size. So another way to make sure that we have a larger surface area, what we could do is to introduce fins. Now, could you see that this surface area is a lot more larger? So if you want to encourage more heat to get transferred over, maybe you will want surface areas to be increased that way. So fins is something that you could implement. But then again, fin is actually not covered in your module that much. It was a little bit in introduction. The lecturer who left Glasgow last year was proposing to introduce more of this fin knowledge, but it wasn't picked up. But just to share with you a little bit of something about fin. Now, although we said that we could increase the surface area using fins so that you get more heat is transferred, but really there's a limit to this surface area by introducing fins. There are things that plays into how effective fins would be, like interfin distance. If it's too close, then it's not so effective. Because usually if you have fin, that means it's naturally convected. You could have false convection. You have seen before audio equipment at the back part of it, maybe there's a fan to kind of like cool the fins down. Those implementation comes with a cost. You need to put in energy so as to remove heat. But if you don't need to put in energy, let it naturally convect, then there is this interfin distance that will come into play. Not be too close. If it's so close as to interfere with the laminar boundary layer, then it wouldn't work. Okay. So another thing is also this thickness of the fin. There's a good thickness fin by the length of the fin that will come into play. And different shapes, types of fin. This one might be a cross-section that's rectangular. This one might be a cross-section that's kind of like cylindrical pins that's coming out. It might be a squarish cross-section. Different cross-sections will offer different surface areas. Okay? But then one important criteria is this length over here. If you want to have large surface area, technically we will put L to be infinity, right? And you get a tremendously large surface area. Not like theoretically that's the way you want a lot of surface area over here. So I have a fin that goes that way and never come back. Infinity. I got that much of surface area over here. But practically, it also doesn't work. Your effectiveness of the fin, and there's a study behind it, there's a certain limited length of which any more further from this doesn't make sense anymore because it's not that effective in transferring heat because your heat don't flow all the way to the end in that way. Your heat will go to the nearest escape route. It will go that way. So that means as we progress along the length, lesser and lesser of this is going to end up with tip. Meaning the more length that you have, the less effective is the fin. So even for that surface area, there's a limit. And how much more can we actually increase the surface area using fins? Actually not much more before it becomes ineffective. So again, surface area good, but good to a certain extent only. What else could we do to increase Q then? We have seen duality, we have seen area. What else could we do? K. K is thermal conductivity. What is a thermal conductivity? That will give us a large Q value. An example of a material would be carbon. What's the thermal conductivity of carbon? Yeah, I know that you say that same number for everything. Alright, I take that. It's a high value, alright, and there are a lot of materials out there, especially metallic material, carbon-based material, that will offer you a very high thermal conductivity. If you want Q to be any larger, that means you're going to use the material. And once you select that material, if you want to increase it any further, you can't do it anymore because you are locked down to that K value, to that thermal conductivity. So after you've selected your material, K is fixed. I'm saying that after that, I want to increase my Q. So what else in the equation now could we do to make sure that we have a large Q? The last parameter, delta X. Delta X would be the thickness of this. Technically, if delta X is 0, I get Q that's infinity, exactly what I wanted, right? I want a large Q value. In order to have a large Q value, delta X equal to 0, but this is not practical, right? If delta X over here is 0, you have nothing over there. And obviously, if you have nothing over there, all heat will get transferred over. Right? Your heat will get just transferred over Q. So, now that we have all these constraints, there's a limit to how much heat to get transferred over by conduction. If you look at convection, you have seen this before. You have convection, heat gets transferred over. Now, if you look at this equation over here, say for example this surface temperature and this ambient temperature, T surface, T infinity, your delta T will be is transferring over, so Ts minus T infinity. What could you do to increase your Q for convection? You said delta T before. The delta T, again, we're faced with that same problem in conduction. Your T infinity, ambient temperature, you can't change it. You can't lower that temperature to encourage more heat that's transferring out by convection. It's fixed. Then how about Ts? Ts would be the temperature of that object. Yeah, you can make it hotter so as to encourage more heat to transfer over, but then usually you start with that object with a certain heat that you want to cool down. It doesn't make sense. I want to heat it up further so as to increase more heat transfer again. It doesn't make sense. So your delta T faces the same problem as this delta T over here in conduction, that you can't really do much to it. Just now after delta T we talked about area. That surface area is this surface area where heat is transferring from, say, this Ts is hotter than T infinity. So that surface area, we could do the same thing as what we have seen in conduction, that we increase that surface area. So if we increase that surface area, again, we can use fins and limit it to the dimensions, effective dimensions of the fin, in order to increase Q. That left us with the last parameter, H. H would be if you have a boundary layer. That boundary layer would have a certain H value, convection heat transfer coefficient, of which we know that the convection heat transfer coefficient is governed by the few things, for example, the geometry, the surface roughness, the fluid properties. Obviously, if you want H to be huge, we could have forced convection across the plate. If you have forced convection, that means you gotta again put in energy. If you want to put in energy so as to increase more forced convection, so as to have more heat that's transferred out, then there is this need to supply that amount of energy to your forced convection to create that fluid current. So we want something that's more passive way, that we don't need to put in more energy so as to have more heat transfer. So again, we're locked now to all these limitations. Then how else could we increase Q more? Given that now conduction, convection sort of sealed our fate, and we can't have a lot of heat that's transferring out based on a fixed setup. This is where this slide comes in and we call it the advanced topics. To summarize what I want to talk about later, have you ever boiled water? No? Still not guessed. Some water. Have you ever wondered one thing if you've seen water boiling? We know that water will boil at what temperature? Right, we learned it a long time ago. 100 degrees Celsius, it will boil the water. Have you also learned some way in your earlier education, what is the temperature of steam? Temperature of the steam? Okay, the temperature of the steam, if you don't know, actually I learned it before in earlier education, 100 degrees Celsius. When I was a young kid, my science teacher told me that I was excited. 100 degrees Celsius. So I gotta be careful if I stand in front of steam when the water is boiling over a kettle. Because 100 degrees Celsius steam can really burn you. So now here comes the part. If you have that water or that fluid, there's water, either in the gaseous state or in the liquid state. 100 degrees Celsius can be in the liquid state. 100 degrees Celsius could be in the gaseous state. Steam, 100 degrees Celsius. Boiling water, 100 degrees Celsius. What's missing here? How could it be that 100 degrees Celsius we have these two things that can happen at the same time? So, if you have been wondering this as you boil water, and you're with me, and we're connected over here. The part about boiling water, that's 100 degrees Celsius, and the part about steam that we could say is at 100 degrees Celsius comes about because when the boiling water changes its state, that state change remains at 100 degrees Celsius. And for boiling water, it's not always necessary that it must be at 100 degrees Celsius. If you go up to the mountain, like what I have done when I was in Japan, went up to the mountain, you try to boil the water, it will start boiling at about 65, 70 degrees Celsius. That's because the pressure up there in the mountain is higher or lower. It's lower pressure up there. If I boil water at a lower pressure, it will boil physically, that bubbling thing. It will boil at a lower temperature, 65 degrees Celsius, 70 degrees Celsius. You can see that it's bubbling thing, but actually it's not boiled yet in our version of boiled. Because we consider 100 degrees Celsius at sea level, we call this boiled water, it's drinkable. So there are certain organisms that wouldn't get killed at 60, 70 degrees Celsius, but you will get killed at 100 degrees Celsius. So if you go up to the mountain, it's boiling, oh okay, let's make a tea now, a cup of tea. You get diarrhea. You get diarrhea. Why? Because the organisms in there is still alive. It hasn't reached 100 degrees Celsius yet. So up in the mountain, you must boil the water a little bit longer so that there's enough time for it to reach 100 degrees Celsius. Or you cover it up in the pressure, kind of like pressure boiler to make sure that it will achieve that. So the part comes when we were talking about if it's on sea level, you have water that's boiling at 100 degrees Celsius and steam that can exist at 100 degrees Celsius. This change of state from liquid to gaseous state, both at 100 degrees Celsius, requires additional energy. How much energy? That energy is about 2,260 kilojoules per kilogram of water. Why this number is special? And this number is only special for, in the case of water, when it changes its state from liquid to gaseous. Why this number is important? It says that if you want to change the state of water, you need to put in extra energy. And during that time, when you put in that extra energy, it's only going all to change its phase from liquid to gas. The temperature doesn't change at all. Now, this will sound very new to a lot of you because I didn't know that when the water is boiling at 100 degrees Celsius, actually not everything will turn into steam suddenly, right? It's still boiling at 100 degrees Celsius. But then it actually requires more energy to convert that liquid state into gaseous state. This, the scientific word for this is latent heat. So you might have heard about latent heat before, and this is exactly what it is. For every material, there will be this latent heat. Latent heat comes in when it changes its state. So the latent heat of vaporization means that liquid to gaseous state. Latent heat of vaporization for water would be the amount of energy that we need to put in to change its state from liquid to the gaseous state. So this is what it is. From liquid to gaseous state, there is this phase change, and it requires, in this case, your latent heat of vaporization. And over here, from solid to liquid, that means from ice cubes to the liquid phase, we call it the melting. Right? So the amount of energy that's required from to change the phase from liquid to gas, that one is 2260 kilojoules per kilogram. The amount of energy that's required to change from solid ice at 0 degrees Celsius to liquid ice that's 0 degrees Celsius, that amount of energy for melting is 334 kilojoules per kilogram of ice. So it works the same way for the ice, that if you have ice at 0 degrees Celsius and water that can exist at 0 degrees Celsius, this change of that phase will require a certain amount of energy. All right? Same as the liquid phase to the gaseous phase. So this one at 100 degrees Celsius and the gaseous part 100 degrees Celsius. So this one sort of like summarizes it. Those numbers that you saw, 2260 and 334 kilojoules per kilogram. Now, you would have seen just now that this arrow is not indicated just in one direction. That means not only from solid to liquid to gas. It can go the other way around as well. So if it's going the other way around, from gaseous to liquid, then at 100 degrees Celsius, that steam, condensing it into liquid, how much energy would need to be removed away from that 100 degrees Celsius steam? That amount of energy would be exactly the same, 2260 kilojoules per kilogram. This is called latent heat of condensation, the amount of latent heat. Have you heard of this English word, latent? Means hidden. So where's that hidden heat? That hidden heat comes about because you have liquid state and gaseous state both at 100 degrees Celsius, and yet you still need to put in extra heat to change its phase. That means there's something that's hidden in there. That's why scientists call it latent heat. So that's going the other way around, gaseous to liquid, latent heat of condensation, from liquid to solid, both at 0 degrees Celsius. We call it freezing. Right? So you have melting over there, it's going the other way around, and we call it freezing. And the amount of energy that's required for freezing will be exactly the same, 334 kilojoules per kilogram. So if we look at the molecular structure, what actually is happening? Where is this extra heat going to microscopically? We could start by looking at the ice in this way. The ice in the form of solid, and note that this doesn't only apply to water that is locked in ice, liquid, gaseous state. It can be metal as well. Metal would have its solid state. At very high temperature, melt into liquid state. Further higher temperature, it will vaporize. It's possible. Yeah. It's just that it's very high temperature. So for any materials, there will be these three states: solid, liquid, and gas. So what is happening in the solid phase? Molecularly, all these atoms or molecules will be locked into a very well-defined crystalline structure. So a crystalline structure need not be a structure that is in the cubic form in that way. Right? And then the next one repeated in that following way. This very crystalline, also a crystalline structure, right? And then etc. It's not necessarily that it must be a boxy kind of thing before we call it crystalline structure. As long as it has a repeating structure, we call this a crystalline structure. For water, in ice format, it has a crystalline structure. H2O, two hydrogen atoms connected to one oxygen atom. If you could just about see it, right? There are these oxygen atoms and two smaller hydrogen atoms to form up the water molecule. So these water molecules are locked into each other at that low temperature. Right? If it's at lower than 0 degrees Celsius, it's still solid ice. Coming to a point that's 0 degrees Celsius, it's still ice. And in order to convert that into the 0 degrees Celsius liquid, molecularly, what's going to happen is that amount of energy that we spoke about just now, 334 kilojoules per kilogram, is the amount of energy to break these bonds over here, so that now the H2O molecules are free to move in liquid state. That is the amount of energy. That is what is happening when you melt ice. The amount of energy that's going in to break these intermolecular bonds between these crystalline structures. Now, if you want to further heat it up, the temperature of this water in 0 degrees Celsius in the liquid state is going to increase its temperature. So these distances will start to get further and further away from each other in the liquid state. So your liquid water, when you heat it up, will actually expand a little bit. The volume will expand a little bit. Just because these water molecules now, they are further away from each other, and because of the introduction of energy from 0 degrees Celsius to 100 degrees Celsius for liquid water, it's going to get more and more agitated. At the point of 100 degrees Celsius, you need a lot more energy now to break them apart. That it becomes your gas, steam molecules. So in the steam molecules, they're going to be just like in air now. It's going to move around randomly in the Brownian motion. We've learned about that before. But to break it away such that this bond, this bond, there's a chemical weapon there, but never mind. If you want to break that bond in between these liquid molecules, you got to introduce a lot more energy. How much more? 2,260 kilojoules per kilogram of water. So that much amount of energy, then it will change, break away its bond and change it from the liquid state into the gaseous state. Right. So we could represent this using this kind of figure. Now, probably you don't have to worry about all these equations, numbers over here. Right. What I want you to take note is that this part here is solid phase. Let me zoom it in. So in a solid phase, you could start at a temperature that's way below 0 degrees Celsius, say minus 10 degrees Celsius. You could increase the temperature. And then as you increase the temperature, you will see that the amount of heat that's transferred to it, Q, will be certain value. At this point, where it's 0 degrees Celsius, you find that the amount of energy that you need to put in doesn't change the temperature at all. So this part over here tells us that there's a phase change. The energy that you put in at 0 degrees Celsius doesn't change the temperature at all. Right? So this much over here, that is your 334 kilojoules per kilogram, that much of energy. Right? So it is used entirely to change the state from your solid state to the liquid state. So at this point here, onward to that point, this is all in your liquid state. This point here to this point here is all in your solid state. So this part here is where you would have your melt or freeze phenomenon. Melt will be if you go in this direction. Freeze will be if you go in the opposite direction. Freeze will be in that direction. Okay. So after you have melted it, over here you can see that that's where you continue to heat up that ice. You introduce further amount of energy into it, so its temperature is going to increase over here to this point. That is your 100 degrees Celsius. So at 100 degrees Celsius, liquid water, if you heat it further, its temperature will not change, because that additional energy that's coming in will change its state from liquid to the gaseous form. So this bit over here, that is your 2260 kilojoules per kilogram. That one is used to change the state, and we call that boiling. If it were to be going in the upward direction, or condensation, it will condense if it goes in the opposite direction. Okay. So once you hit the gaseous state, you could still put in your energy, kind of like have it in a lockup in this container that wouldn't allow the steam to escape. And you can still heat it up further. right? So it's still going to be air, the water molecules that's going to be contained inside. And then you could still heat it up further. So this one will still go on and on. Okay. So the important part is that you could recognize there is this latent heat, right, between the solid to liquid phase and liquid to gaseous phase. So this is important. And in order to indicate the importance, I will put a star. Right. That's because it's important. So let's have a look at why do we need to talk about this in the advanced topic here. There is a need for that because there is an important property that I'm exploiting. If you recall, we wanted Q to be as large as possible. And we kind of like walk through it. Well, there's actually a limit. We can't really have a lot of heat that's transferring over because of the limitations that we heard about just now. This latent heat of vaporization is going to get away, it's going to remove a lot more heat from the system if you could make that system change its phase. You can change its phase usually from the liquid state to the gaseous state because that amount of energy that is taken up for that phase change is 2,260 kilojoules per kilogram. That's a lot of energy. That's very useful. I can have something that exploits this property. So we'll have a look at what is that something. I'm going to start by looking at this cooling tower. Now this cooling tower, this is a real view of that, but let's look at the schematic view of this. In the schematic view, your cooling tower, as what it suggests, is to cool, right? So what is it that's cooling? The hot water is going to come in from here. You have the hot water coming in. This whole thing over here is your tower. And lined up at the top part of the tower, you have a lot of sprinklers that's out there. These sprinklers, not atomizing yet, just sprinkle the water. These sprinklers, they are going to sprinkle this hot water and drop it down from great heights. Right? You might have seen cooling tower in some of the air conditioning units in near Poly, right? Especially the part that's just opposite the marketplace. Yeah, there are some cooling towers over there. But if you have not noticed it, maybe something else could help you to notice it. At the top of the cooling tower, there's this fan. This fan is sucking out the air, such that when you pass by that place, you could feel that there's some kind of hot, moist air. Right? I felt that before. It's pretty uncomfortable to walk past that place. Do you know which place I'm talking about? This, we have the Mountain Place. SIT building is here. And there's this road that's leading down that way, arcing. Yeah. And Sakai Sushi is here, I think. Right. And then there's a zebra crossing over here. There are some cooling things, cooling towers over here. Remember? Some staircase that's leading down. Yeah, that place. Yeah. If you know where, if you know what I'm drawing, but have never been to there before, it's like some dark alleys everywhere. I've never been there before. You can drop by a little. It's not so dark. So the cooling towers. The cooling towers would have the fan at the top, so it's going to draw air, the ambient air from here. And normally this ambient air should be dry air, but if it's not dry air, dry, cool ambient air, that's fine as well. The humidity in Singapore is pretty high, so sometimes it's described as we are swimming in the air in Singapore. It's so humid. The humidity is pretty high. if you have air that's coming in here, these sprinklers, they are sprinkling hot water downward. You can see that this sprinkled hot water will interact with the cool air that's coming up. And this cool air, they are going up, that's because there's a fan here drawing the air up. So you could look at this as some form of heat exchanger. And in this case, is this a parallel flow or counterflow heat exchanger? It's a counterflow heat exchanger. So we know that this hot fluid or hot water that's sprinkled down eventually will drop to the bottom of your cooling tower as cooled water. And since it's cooled water, we can take it out there and go to where heat would get exchanged. And then hot water will come back in. And then you have this continuous circulation for your cooling tower. Okay. So this place here may be your air conditioner, because your air conditioner will try to produce one side is cold, the other side is hot. So this hot side sometimes is cooled down by water, or sometimes it's just natural air convection. If it's cooled down by water, then this heated up water over here got to be cooled down using cooling tower. So you could see what is the energy consuming or electricity consuming device that can happen in a cooling tower. It's pretty much of close to a passive device. You don't need to introduce more energy into it in order to chill it down so that the water now, the hot water will be chilled down. You don't have to do that. You just drop it down as a sprinkler from a tower that will get cooled down. You collect it up. The pumping energy that you use to circulate this is the only electricity that's required for the system. Making a large volume of hot water that can be cooled down pretty much effectively. If you have a huge volume of water that you want to cool down, you could put refrigeration, whatever it is, that's going to consume a lot of energy. Or you take that, go to a huge tower, sprinkle it down, just like that, and it will get cooled down by the ambient temperature. So this sort of cooling tower is very desirable. There's also another way to cool things down. We call it the evaporative cooler. Now the evaporative cooler works in this way. You have a discharge over here, and this discharge is caused by a blower fan that's over here. This is your blower fan. So the blower fan will take in air from the ambient to come in the following way. Right. So this is kind of like a centrifugal fan. The centrifugal fan will suck the air to come in and then exhaust out in the following way. And coming in between this hot, dry outdoor air is this thing over here. This one is made of wood wool, and we call it the evaporative pad. But why is it evaporative pad? That's because we kind of pump water, a little bit of water, pump it up, and then get it distributed with kind of like trickling drip into this wool. So you could imagine that this wool now is wet. Right? If it's too wet, then you'll flow down and then you'll get trapped over here. And then the pump will just recirculate to make sure that this pads there, this woolen pads, is always moist. If it's moist and you have the outside air that's hot and dry, just like in Singapore, or maybe not dry but hot, this hot air is going to pass through the wool because there's suction by this blower, and then it will exit over here. So the important part is that as the hot air interacts with the wet wool, that hot air will get cooled down, pretty much like the cooling tower that you saw just now. Just that it's not dropped in great distance, but this happens across the thickness of the wet wool. So if hot air were to pass through, you will get cooled down and then you will get sucked out. So whatever that's exiting over here will be cool, humid air. You will definitely get cooled down because you would, there is this vaporization from liquid state to the gaseous state because hot air is going through. So as it changes its state, it would remove a lot of energy. How much energy? 2,260 kilojoules per kilogram. That much of energy to change the state from liquid to gaseous state. So this is good because that amount of energy that has been removed from this hot outdoor air now has been cooled down, and no doubt it's going to be a little bit moist. So you have the cool, humid air that can be pumped. And in fact, you have seen before some of the fan, they no longer call themselves as fan, they call themselves as air conditioner. And when you buy it home, you put it in front of you, they say, put in a little bit of water into this fan. And then you just stand in front of it, and then you turn it on, start to feel, yeah, it's a bit wet now. I feel a little bit cool now, yeah. So what was it? It's actually trying to sprinkle some of this water as the fan would blow toward you. Sprinkle a little bit of that water so that the water would be transported in the air. If there's too much water, then your face is going to get a little bit wet. So normally you'll adjust it such that the amount of water that's going to land on you will be minimal. But the idea is the same. It wants to remove heat from your body so that you can feel cool. How much heat? The amount of heat that requires the liquid state of the water to change into gaseous state. 2,260 kilojoules per kilogram. That amount of energy can cool you down. Okay? So this kind of principle is very similar to that. But I have not mentioned something that is critical yet. The critical part comes in heat pipe. Now, if you look at my this tablet over here, could you see it's kind of like very thin, very thin. And actually, at this vent over here, I'm not sure could you see it. There is a vent here. That there's a centrifugal fan that will blow the hot air out. Now this hot air, where it came about is because there's a microprocessor in there that's turning on this power point, consuming, is processing the microelectronic chip. And because of that, that chip gets heated up and is required to be cooled down. If we don't cool down that chip, what's going to happen is that that chip is going to melt down, seriously. So we need to cool it down. But then if we have such a small little tablet over here, we can't really implement something like a cooling tower here. No, right? A fan blower here that we need to put in water. No, right? So what is actually happening in there? If I were to take this tablet apart, this kind of picture is going to come to you. Right? Particularly this coppery looking pipes over here. This one is called heat pipe. Heat pipes. The topic of heat pipe is important. What is heat pipe? How does it work? Why do we need heat pipe? It works in the following principle. This is one typical section. It's going to be long, so it has been truncated in the following way. The heat pipe works in the following way. Maybe before describing how it works, let me describe the components. This middle portion here has got a certain fluid. Usually we'll have heat that's entering over here, and normally this heat that's coming in is coming from your microprocessor. I'm going to write it that way, microcontroller, MUC. The microcontroller is going to get heated up, so you place this heat pipe above it. This heat pipe would have a certain shell around it. Usually this shell is made of metal, and you could find various metal, but let's use copper because just now you saw in the figure, it looks like copper thing. So this copper shell seals up this kind of like bluish region, the grayish region. This part here is called wick. The first time you saw wick in your earlier education, it refers to candle. Yeah? Very similar to that, except that it's not made of candle wick as cotton material, but it's made of metal. So I'm not sure if you've seen in your kitchen, there are some of the scrub that you use for washing dishes. Some of it comes with it, green pad, right, that kind of scrubber. But some of it comes in like a coil of metal, you know, a metal scrubber. This wick is something like that. Metal wires, a lot of it, that forms up the wick part. Right? So this wick has a purpose, but I'm just introducing you different components, and then I'll tell you what are they doing. Oh, it's actually written over here, wick. So the casing over here. Now there is a cavity that exists within the wick. This cavity is important. This cavity is actually filled with a liquid that can change its state. Change its state from liquid phase to gaseous phase. And you would want to choose a liquid that can change its phase at the temperature of the microprocessor. Why is that so? If I were to put water as a liquid over here, and we call it a working fluid. If this working fluid were to be water, in order for the water to change its state from liquid phase to gaseous phase, the temperature would then need to be 100 degrees Celsius. Now we can't have our microprocessor in there that reach 100 degrees Celsius, or else we'll melt down some of the smaller components in there. So we need a fluid that will vaporize at a lower temperature. A fluid, say for example, alcohol. Now alcohol will vaporize almost at close to about 40 degrees Celsius. If I were to fill in this heat pipe over here with alcohol, what's going to happen is that if I place this side of my heat pipe to a microprocessor, the microprocessor's temperature is going to increase. It's going to heat up that alcohol, and then that alcohol is going to vaporize pretty much quickly because it doesn't take much higher temperature to vaporize it, just about 40 degrees Celsius. Vaporize it, and then once it's vaporized, it's going to travel to the other side. So now, all these components I've discussed already. Let's talk about that process that I was talking about. If this alcohol here would vaporize, it will get transported. And why is it that it will get transported over the other side? That's because over here, as that liquid alcohol would vaporize, its pressure is going to increase. Once this pressure increases, this pressure here will be lower. So naturally, the vapor alcohol is going to move from this end to the other end. Now the important part is that this other end over here is good to have cooling fins over at this side. Why cooling fins necessary? Because in the function of a laptop, you would want to have a blower fan over here so as to blow the forced convection across in that way. Now, that will be using the ambient air that's coming in. Ambient air, say about 30 to 32 degrees Celsius. If I would have forced convection that's happening across, once this heated up alcoholic steam comes over here, or alcoholic vapor comes over here, you will experience a drop or this removal of heat because there's cooling fins over there. And once it's cooled down, it will convert back into its liquid state, and then it will travel itself back via the wick naturally to this part here to get reheated up. So you could see this entire process over here will just continuously circulate. Right? But why is this important? Why can't we just put a copper tube? A copper tube would need some time to be conducted away. The amount of energy that can get transferred, we have seen in the equation of conduction, is limited. This one here would remove a lot more heat away from the microprocessor. A lot more. Why? Because there's a change of state. Why is change of state that important? It's because whenever there's a change of state, it requires a lot more energy. In the case of water, 2,260 kilojoules per kilogram. For alcohol, it will be a different value. But we know that as long as there's a change of state, there'll be this latent heat of vaporization that's going to occur. And whenever there's latent heat of vaporization, it would remove a lot of heat. That is exactly what we want. We will want to introduce more forced convection so as to cool it down. No, we don't want that. We want real heat to get removed away from the microprocessor. And this heat pipe is a revolutionary invention for a small form factor just like your laptop. That's why we can cool down this microprocessor in the laptop in a very tight space, and we can route this heat pipe to another location that is at the site of your laptop, and then you have the forced convection to cool it down using ambient air. So this topic of heat exchanger, this heat pipe is important. For your heat pipe, the transport of latent heat energy makes heat pipes very efficient. Now, how much more efficient, how effective it is, actually is 100 times much more greater than if it were to be an equivalent copper rod. That means that same volume of heat pipe, if I change it to a copper rod, your heat pipe is more effective than that copper rod. How much more effective? It's 100 times more. Why 100 times more? Because why that many times more? That's because of the change of state of the liquid. So we're exploiting this property of phase change from liquid to gaseous state, the latent heat of vaporization. We're exploiting this property to remove the heat from the microprocessor. So there's one question that I always ask for every cohort, and the student who could answer that over the year turned out to be kind of like close to one of the top students in class after the exam. So the question is this. Okay, give it a try. But no guarantee you'll be top student after this question. This laptop that I was saying this mechanism of heat pipe that I was saying resides in your laptop. Now, while I was saying that it's possible for this cooled down liquid over here, after the forced convection over here, it will cool down that alcohol vapor, cool it down into the liquid state, and then you move back via the wick into this hot region again. Move back. Just now I said automatically. What happens if I have the laptop that I place it upside down? So now it's upside down. It doesn't like that. If I place this upside down, how can this liquid alcohol that has condensed move back to the heated pipe via the wick? What is the action that's happening over there? I don't have a pump to pump it back. All this is closed up now. It's a sealed system. So how do you think this liquid could flow back, even though I have my laptop able to function at various orientation? I'm not using gravitational pull. Yeah? If I'm using gravitational pull, if I pull it this way, then yeah, it will flow down in that way via the wick. But I think my laptop can still work if I place it the other way around. So what do you think is the phenomenon that's happening over there? I can hold my laptop here, that laptop, Apple laptop over there, hold it upside down. It will still work and it wouldn't overheat over there. It's using heat pipes, I'm pretty sure. That's the cooling system over there. But why is it that that cooled down working fluid can flow back to its heated cell? What do you think? It's because of the capillary tube action. So capillary tube action refers to what property of the fluid? It's talking about what? What is the property that of the liquid that capillary action is exploiting? Why is it that capillary action could move? What? Density? No, it's not density. It's not a pressure, because if it's pressure, we already said that this is higher pressure, this is lower pressure here. It shouldn't flow from a lower pressure to a higher pressure, no, right? Always that if you have a pressure difference, it's higher pressure flowing to lower pressure. So what is that capillary action? That is correct. And what is that property that allows this to happen in a liquid like alcohol? Have you seen in Singapore those pedestrian overhead bridges? Have you ever seen what is below the bridge after a rain? Right? Do you see that, hey, under the bridge it's kind of like wet, yeah? Even though the rain is falling from the top, but why is it that it's wet at the bottom? Not completely wet, but you have trickles of water going to the underneath part of the bridge. So what is that action? Why do you have the action? That's because of the surface tension of that liquid. Right? If you have capillary tubes, why is it that it's able to flow? That's because of surface tension of the liquid. Surface tension is if you drop a drop of water, it forms this shape. It doesn't form like that, right? Because there is a surface tension. So surface tension in capillary tubes, or in this case, wick. Right? So the wick will be something like that, a mesh of wires. You can see that there's some holes in between here. The surface tension will make sure that over here is more attractive to the working fluid that's filled up over here. So naturally, using surface tension, capillary action, that liquid will flow from this side to the other side. Automatically, a self-sustained passive device that doesn't require external energy that's put in to drive it in. Hence, very efficient. Let's go for a break.